Hello everyone, you're on a pick of the week, that specific selection of interesting and challenging problems related to different aspects of maths. It may vary from GCSE level, basically from 14 plus years, and up to university maths. So here is the bright example of university maths. I represent the concepts of limits. However, we are not going to go through define the limits of different functions. Vice versa, we actually need to prove that some specific functions fails to have limits. And this is the right time to explore. Let's have a look at the set of problems that you're challenging with, okay? Hope you'll be able to solve that. That's definitely students who are already aware of limit concepts. Only in this case, you can start solving that. For those who are just start doing limits, I'll just give some definition of limits. We'll consider one hand and right hand limits, basically one-sided limits. And after that, we just move on to clarification how exactly to show that those functions fail to have limits. All right, if you're ready, let's get started. All right, so let's have a look at what limit is for a function. Let's say we have function fx and it's defined on an open interval about point x0, except for x0 itself. So for some reason, it might not take the value x0. So basically, f from x0 might be undefined. In this case, what we understand as the limit. So L is going to be the limit for the function fx if the value of the function fx is very close to L when the argument of this function tends to x0. And this tendency might be from any side. So from any side. So in other words, if we have straight line function, let's say fx, let it be identity line. So this is fx, and we want to take x0, the value for this point, so that we want to investigate the behavior of this function around this argument, around x0. So simply we can say that if we take some surroundings, a small range around 2, we understand that the function value tends to close specific value L, which is in our case equals to 2, by saying that the argument tends to x0. So in this case, we actually touch their one-sided limits, because if we approach from this side to 2, we understand that function value start closer to the value of L equals 2 from below. And the same way, if we have x tends to x0 from the right side, just basically values a little above 2, our function will tend again to the same limit L equals 2, to the same value L equals 2 from the top. And that means we can say the following. So we can ensure that in our case, we can say that we can make our value for the function fx be very close to L, which is in our case is 2, by taking our x values very close to x equals 2, by taking our value very close to x0 and from both sides. Okay, so this idea is pretty straightforward, and that means from here we can come to more formal definition. Let's say your function fx again defined an open interval about x0, except for x0 itself. So if we can take for any epsilon more than 0, there should be some delta, another just number delta, non-negative, basically positive in this case, so that for x minus x0 smaller than delta, function value fx minus L be within epsilon. Okay, so what it means that for every randomly chosen number epsilon, we can take a specific number delta, so that this surroundings, basically x0 plus delta and x0 minus delta, will ensure that the fact that the difference between function fx and the limit itself L be within epsilon. So in other words, we can take the value epsilon, so that our function value will be within the limited range L plus epsilon and L minus epsilon by adjusting our delta. Okay, so that's what it said by formal definition. So maybe a formal definition a bit weak, especially for those who start learning the limits. But I think the idea is pretty straightforward. That comes from informal definition, so that we can ensure the value of the function fx be very close to L for values x close to x0. All right, so maybe just a bit more examples to understand what limits are. So if we take the same straight line, except for the value x0 equals to, let's say, 2. So this function cannot take this value, and instead it will take 4, for example. We can define this function as piecewise. With continuous function, I think is pretty much more obvious that they do have limits in every single point on the domain. But with a piecewise function and function with gaps, it's more obvious. So that's why I decided to demonstrate using piecewise functions. All right, so this is our fx. So we can define fx as simply x for any value of x except for, let's say, 2, except for 2, x0 equals 2, and let's say 4 when x is 2. In this case, value x equals 2 is forbidden value, so it's out of domain. But in order to define somehow, we need to use the piecewise function in order to define f value when x is 0 equals 2. So in this case, we have basically gap. And how to explore, does this function have the limits around x0? So by definition, so fx need to tends to some L value when x is very close to x0. In our case, x0 is 2. And indeed, if we explore from both sides, right, and if we explore the left side limit or left-hand limit for values tends to 2 from a little below 2, so we understand that function value will tends to 2, right here. And the same way we can define, so the limit, that was limit left hand limit when x is very close to 2, but from the value is a little below 2 itself. So we understand that this limit becomes 2. So we can pick up values for x very close to 2, so that to ensure that f value, function values, will be close to 2. Okay, so and from the right hand side, so right hand limit, in this case limit when x is very close to 2, but from values a little above, from here, from that side, our function will tend to 2. Hence, both limits, left hand side and right hand side limit, are the same, and hence we can say that left hand side limit is equal to right hand side and its values, and that means that it's going to be 2 equal L, which is 2. So in our case, the limit of the function nearby the region x0 equals 2 becomes L equals 2. However, the function itself, f from 2, will have quite a different number. It's going to be a 4 in comparison. So for those gap functions, the limit does exist. Also, I'll just give you another example when we have a piecewise function and let's say from one hand side it goes in this way, and that's for x less than 0, and for values more or equal than 0, so this point is excluded, the whole point, and for x equals more or equal than 0, it's going to be the straight line also that goes in this way. So what we can say, that if we want to investigate our function fx, which is set up as 0 for x less than 0 and as 4 for x more or equal than 0, we can explore the concepts of limits from left hand and from the right hand side. So this is right hand limit, and obviously it will tends to 0 from values a little above 0 itself. We understand that fx in this case tends to 4. Okay, while if we explore the limits, which is left hand limit, if x tends to 0 from left hand side, okay, that's why we denote minus on top as an index, our value function will tends to 0, so that means fx tends to 0. Because one-sided limits are different, in this case we believe that there is no single value for one-sided limits, and that means the limit doesn't exist. So hope this clear examples actually shows you the idea that for our function gx we also have pretty much the same. So we have y, or in this case g, equals 2 for x more equal than 0. So, and 2, it's not a whole point, it fill-in point, that's 2. And obviously from right side, so right side limit is going to be, is going to be 2 when x tends to 0, right? From positive side. While our function also defined here, and this is the whole point, when we explore the left side limit, we understand that g value tends to 0 when x tends to 0 from values a little below. So that definitely this limit this function doesn't have a single value limit for one-sided limit. So that means we don't have any limit at all around value. So g from x fails to meet the limit, or basically it doesn't have. So it doesn't have limits for limit when x tends to 0. Okay, because two limits are different values, one-sided limits are different values, and that means it has a gap. All right, hope you understand that. Let's move to the next function and let's explore how it looks like. So first I just put this and draw the graph of it. So this function is hyperbola, and if we explore the tendency when when x tends to 0 from one side and from another side, x tends to 0 from values a little above, we understand that function's value tends to basically infinity here, positive infinity here, while here the tendency is to negative infinity. Because again, one-sided limits don't have a single value, we can state that there is no limit. However, the function can intake the value right here because f from 0 is defined. Okay, f from 0 is just simply 0. It's one single point. However, the general behavior for values, for like x values a little above, completely different from that value. They they ensure the function fx to be positive and negative infinity. So it grows too large to have a limit. So that means gx also doesn't have a limit. Gx doesn't have a limit. Okay. So basically, they don't stay close to any real number, because infinity and negative infinity, they're absolute numbers, but you understand that if you take, for example, for 1 over x values like x 10 to the power 10 or 10 to the power 100, you'll get your g function be very close. Oops, my bad. Of course, negative powers, yeah. Negative 10, that means it's very close to 0, as well as 10 to negative 100. It's pretty much closer to 0. So our function 1 over x will be closer to quite big numbers like 10 to the power 10 and 10 to the 100. 10 to the 100. While, for example, left branch of this graph will tend to the same values but with negative signs. So that means they're quite completely different numbers and no single value for both sides. Okay. Let's have a look at the last example. So we have function s from x, which is defined as sine 1 over x for x positive range and 0 for x less or equal than 0. So basically the left hand side of this graph is going to be like this one, okay? And 0 itself. So 0 itself. Okay, so that's for x less or equal than 0. What we can say about this function and its behavior around or about s from x, about x 0, which is in our case 0, because we explore tendency to 0. So as you understand, so by graphing this function, you understand that for the range, or for the range for x more than 0, this function behaves like oscillator, and the closer x values to 0, the more frequent oscillation occurs with this function. So what it means, oscillation, it means that the period will shrink and frequency will increase every time when x tends to 0 from positive side. And what's actually happening in this case? The function value basically commutes from -1, from this value to that value. And you cannot like predict where it's going to be on every single step x, right? It might be like s minus 1 and s1 and somewhere in between. So basically this oscillates too much to have the limit, because again, there is no single limit L. There is no single limit L as x approach to 0. So limit basically every time changing between -1 and 1. So that means right-sided limit doesn't exist. Okay, while left side limit does exist, because in this case, when x tends to 0 from negative side, the value of the function sx tends to 0. While from here, it commutes between -1 and 1, and you cannot predict the value. All right. Maybe it's better if you compare this behavior of this function, oscillating function, with the function that do have limits. For example, if you take sine 1 over x when x is very close to infinity, and you just take discrete number for x, let's say quite big numbers. So what will happen? Sine of 1 over infinity simply becomes, let's take indeed 10 to the power of 10, or basically 10 to the power of 100. It's quite big numbers. Obviously, you'll have your fraction 1 over x to be very close to 0. So basically, it becomes sine of 0 and sine of 0 delivers you value of 0. So set of points gradually approach their x-axis, a horizontal asymptote in this case, and set of numbers becomes very close to one number. Okay, so I hope you understand that in this case values approach to a specific value, which is 0 in this case, while here during oscillation you cannot predict the single value. That's why right hand side limit doesn't exist. Hope I clarified that. You may just take some random numbers, maybe specific numbers, so that as from x1, x2, x3 will take values like +1, -1, +1, -1. It's pretty easy to get. Let's say 1 over x, you can take x value as let's say 2 over pi and just plus the period 2 pi n if you like. Okay, xi's. Also to get, so this in both cases you'll get +1. If you take another values like 2, let's say 2 and 3 pi plus 2 pi n, you'll get -1 values. And by increasing n to infinity, you actually, for this set of numbers you'll have 1, and for this sort of numbers you will have -1. So you can never predict which exact value the function will take. Okay, so hope you understand this concept, and hope you got basically 3 categories of functions which fails to have limits. So like sort of jump function with a jump, or unit step function, or in this case 4-step function, and basically it has a gap, and we explore it from positions of limits, one-sided limits. Here what we have, we explore a function that goes to infinity, basically grows too large to have limit. Okay, and both limits will tend to different numbers, absolute numbers, infinities, but they are different signs, so that means definitely there are different numbers. Okay, and also we explore a function that oscillates too fast or too much to have a limit. So I hope you clarified my explanation a little bit, clarified your questions about these functions, and hope that you'll be able to provide the same analysis for your problems. All right, if you're new here, please subscribe, share this video to anyone who's struggling with math. That was Daniel Dallas, and see you next time.